Good morning, students. So in the last class, we have discussed about some of the measurements. That is measurement of output resistance, and as well as measure how to measure the output resistance, how to measure the total output offset voltage, and also we have discussed about how to measure the slew rate of for an operational amplifier. So we have observed the DC characteristics and how to measure those DC characteristics. So we have observed that in the last class, and now we are going to discuss about the stability in operational amplifier. And also in the last class, we have discussed about the frequency response of operational amplifier also. Frequency response of operational amplifier. So coming to this frequency response of operational amplifier. So how this operational amplifier is going to work, that is going to perform its operation as an amplifier at different frequencies we have observed. So from this graph, we have discussed that due to capacitance effect, there will be three corner frequencies, that is F1, F2 and F3. So why these three corner frequencies means, these three corner frequencies due to four blocks in an operational amplifier, as we have discussed in our first chapter. That is the four blocks: the first stage, second stage, and third stage, and fourth stage. Between these blocks there will be three connections. So from 1 to 2, and from 2 to 3, and 3 to 4. So between these two stages there will be a capacitance effect. So because due to those capacitance effect, here we are going to obtain a three corner frequencies, that is F1, F2 and F3. So F1, up to F1, the op-amp is going to behave, the performance of the op-amp is, that is the performance of the op-amp is better. You can see from this graph. So that is, it remains, the gain remains same from 1 kilohertz frequency to up to F1, you can observe from this graph. So whereas when you are going beyond F1, so the frequency, that is the gain, is going to drop by minus 20 dB. So there you can observe that the gain is going to drop by minus 20 dB from F1 to F2. Up to F2, it is going to drop by minus 20 dB. So F2 is the corner frequency due to the passing of signal from second stage to third stage. Again, there will be a capacitance effect. So due to that capacitance effect, there will be a attenuation. Again, there will be attenuation, that is minus 40 dB attenuation. That means the signal is going to lose its strength. So the reduction of strength of the signal as frequency is going on increasing due to capacitance effect. So beyond F2, the signal is going to lose its strength by minus 40 dB. And after that, we are going to the another frequency, that is corner frequency, that is F3. So F3 is due to the capacitance effect when the signal is going to transfer from third stage to fourth stage. So this F3, beyond this F3, there will be a attenuation of minus 60 dB. So these three corner frequencies is going to reduce, that is reduce the frequency response of operational amplifier. So This is the main. This is the operation of operational amplifier. That is the performance of operational amplifier at different frequencies. So why this is going to happen means due to capacitance effect. Whereas coming to the when we are going to operate in a closed loop configuration, so we have observed the thing that is so here we have observed the closed loop operation of op-amp. So when we are observing this closed loop operation of an op-amp, the gain, the closed loop gain is going to become, so loop gain here is see AOL into beta is the magnitude of the loop gain becomes 1. So when such a condition occurs, there will be a phase shift of the signal which we have given as an input, and also there will be sustained oscillations. There will be a sustained oscillations. That means here our operational amplifier must work as an amplifier, but practically due to this reason, this loop gain is equal to 1. The op amp is not going to behave as an amplifier, it is going to behave like a oscillator. But this is not the correct performance for an operational amplifier. So for that reason, so we are going to discuss about the stability of an op amp. That means at what conditions this operational amplifier is going to behave as an amplifier, and this operational amplifier is going to behave that is perform better, it gives its better performance. So that we are going to observe. So for that reason we are going to consider the stability of an operational amplifier. So we are going to consider the stability of an operational amplifier. Here when we are considering, the stability of an operational amplifier, when we are considering the stability of an operational amplifier, so see for that we are going to consider the circuit which we have shown here. So which is having two signals which is given to an operational amplifier, that is V1, the voltage source V1 as well as the voltage source V2. Whereas for inverting terminal, that is for inverting terminal we have given a feedback and we have given an input, and for non-inverting terminal directly we have given the signal itself. So see here, for observing the performance of an operational amplifier, we are going to make these two voltages either zero level means nothing but making, we are making that terminal to be grounded. So ground potential is 0. So we are making one of the terminal 0 and making another terminal, we are giving a source to the another terminal. So we are observing the performance of this operational amplifier. So for that, so we are going to consider this resistive feedback network for an operational amplifier, and we are going to observe the performance of this operational amplifier. So coming to here, the closed loop transfer function, as we have obtained the closed loop transfer function, we have seen in the last slide itself. So ACL, the closed loop gain, which is equal to open loop gain. Here A is nothing but the open loop gain divided by 1 plus A beta. So beta is the transfer function, feedback transfer function, as we have studied that. Beta is the feedback transfer function, and here the closed loop voltage gain, which is given by ACL, is equal to, it is a ratio of open loop voltage gain to the 1 plus A beta. So as we have observed that 1 plus A beta is equal to 0, then A beta magnitude is going to become 1. When such a condition occurs, the op amp is going to become unstable. That means it is going to produce oscillations, as we have already discussed that. Since here we are going to consider a feedback network as a resistive network, that means we are not considering any capacitance or inductance effects. So we are going to see that it does not provide any phase shift. As we have seen in the last slide, there will be a phase shift of minus 90 degrees also due to this loop gain. So here we are using a resistive network, Since resistive network does not provide any phase shift, so here we are considering that here if an op amp, here we are using op amp in inverting mode, then it provides a 180 degrees phase shift. So inverting mode means when we are giving input to the inverting terminal of an op amp. So when we are giving input to the inverting terminal of an op amp, that is inverting terminal is nothing but negative. There you can see in the uh, diagram, that is the negative terminal of the op amp, that is the inverting input. If we give any signal to the inverting input for an operational amplifier, then the output obtained will be a 180 degrees phase shifted signal. So this, how we are going to observe this phase shift at high frequencies. Due to corner frequencies of operational amplifier, there will be a phase shift of minus 90 degrees for each corner frequency. As we have observed in the last slide, there will be a phase shift of 90 degrees. And for some beta values, the magnitude a beta becomes in unity. That's what we have observed in the last slide. So if a beta becomes unity, then what happens? A beta becomes unity, then it is going to produce the oscillations. That means loop gain is unity, then the circuit is going to produce the oscillations. That means the op amp is going to produce the oscillations. This is called instability. So this is called instability of an op amp. So for how this instability can be eliminated, how to overcome this instability, now we are going to see that how to overcome this instability. So this instability can be overcome by observing the response of this operational amplifier. So see here, at low frequencies, here you can observe at low frequencies, the additional phase contribution of, that is, open loop voltage gain is 0. So a beta greater than 0, that means ACL, that is closed loop voltage gain, closed loop gain must be less than the open loop gain, then the system must be stable. That means this depends upon beta value also. So this loop gain is depends upon the beta value. So where this beta value is going to depend upon R1 and R2, as we have studied that this is a parallel combination of R1 and R2, nothing but. So by adjusting this beta value, we can maintain this loop gain. So how to maintain this loop gain? How and what must be the value? Beta value must be what for performing our operational amplifier better. So that we are going to see now. So at high frequencies, the system A is having three corner frequencies due to RC pole pair. So A must be having a phase shift of minus 270 degrees phase shift. That means here we are going to consider three corner frequencies. Each corner frequency is going to phase shift 90 degrees. So three corner frequencies, 3 into 90 will become so minus 90 degrees. That is 3 into minus 90 is nothing but 270 degrees phase shift will be there. So then a beta becomes negative and instability occurs. There will be instability in the system. So here you can observe the curve due to different frequencies. Here you can observe the dB, that is gain on y-axis, and frequency on x-axis, and you can observe from this diagram, you can observe the response of the operational amplifier. So for example, if the closed loop gain of an operational amplifier is 80 dB, then the bandwidth is approximately the bandwidth means here you can see. So this is the 80 dB. The closed loop gain for an operational amplifier is 80 dB. Then the bandwidth will be around 600 kilohertz. So see here, first line. So it is around 600 kilohertz. So below 1 megahertz, below 1 megahertz is around 600 kilohertz, and we can say that the phase shift is added. So at this is a single corner frequency, there will be a phase shift of minus 90 degrees of the signal. and the open loop gain is here A, the amplifier will remain stable. So because of this single corner frequency, here the gain remains constant up to this corner frequency. Hence we can say that the operational amplifier is stable at this point x. Here this is the point x. Here we are going to consider this point as x, and this at this point the operational amplifier which we are considering is stable. The operational amplifier which we are considering is stable at this particular point. So see here, you can observe from this graph that this is the 80 dB line, and this is the frequency response curve, and here around at 600 kilohertz. So below 600 kilohertz the op amp will be stable. The op amp will be in stable state only, not a not unstable. It is only in stable state. And next, when we are going to consider the closed loop voltage gain as 60 dB, this is the 60 dB line. You can see here, this is 60 dB line. So this line is going to intersect our response, our frequency response of our operational amplifier at point Y. So we are going to take this point as Y, and this at this point Y, from by projecting this point Y onto the x-axis line, so we are going to obtain a frequency of around 3.5 megahertz. So see here, this is 1 megahertz. So you can observe here, so this is 1 megahertz, 2, 3, 4, 5, up to 10. So this is going to coincide at 3.5 megahertz. By observing that, so approximately we are going to consider that. So by observing this, so we can say that the operational amplifier is going to perform, um, that is here it is nothing but the second corner frequency. So how this operational amplifier is going to perform here? So here there will be a phase shift of because of second corner frequency already at the first corner frequency there will be a phase shift of minus 90 degrees, and this here due to second corner frequency, again a minus 90 degrees phase shift will be there. So minus 90 totally there will be 180 degrees phase shift, minus 180 degrees phase shift of the signal will be there at a point Y. This is at point Y, and the circuit is likely to be unstable. From this point, the circuit is going to become unstable. So, and next when we observe the third corner frequency, which is going to occur at a 20 dB gain. So see here, this is a dotted line what we have drawn here. So this is going to intersect our response curve at point Z, our response curve at point Z. So at point Z, so there will be a third corner frequency, and the attenuation of the signal is minus 60 dB. And at point Z, we can say the phase shift will be minus, that is minus 90, and minus 90. So totally minus 270 degrees phase shift will be there. So by considering this response, we can observe that the op amp is going to become unstable when it is beyond the point X. So when it is um, going to cross the point X, that is when the frequency is more than this point X, then the op amp is going to be unstable. So we can observe how to adjust this stability criteria, uh, how to obtain the stability criteria. So how to obtain the stability criteria we are going to see now. So the transfer function of the op amp here, by observing this graph, the transfer function of the op amp is going to depend upon three corner frequencies. So we are going to write that the three corner frequencies in S domain. So as we have written here, here you can see in the S domain we have written here already. So here you can see the gain which is equal to the closed loop voltage gain, which is equal to open loop voltage gain into omega 1 divided by S plus omega 1. So this is due to single corner frequency. So using this same equation, there we are considering the three corner frequencies. So we are going to write the equation for three corner frequencies, the equation of closed loop voltage gain with three corner frequencies. So here we are going to write the equation for three corner frequencies, and we are considering here the op amp is going to operate in inverting mode. So for that reason, so the gain is going to become A is equal to, here negative symbol is due to we are going to use here operational amplifier as inverting amplifier. So we are giving input to the inverting input of the operational amplifier. So then the output will be in the gain will be in negative. So here you can see the negative symbol indicates that there will be phase shift between input and output. So A is equal to minus AOL into omega 1, omega 2, omega 3. AOL into omega 1 into omega 2 into omega 3 divided by S plus omega 1 into S plus omega 2 into S plus omega 3. So where 0 less than omega 1 less than omega 2 less than omega 3. So here the closed loop voltage gain A is going to depend upon open loop voltage gain and the corner frequencies, that is omega 1, omega 2 and omega 3 also. So by seeing this, we can write the poles is going to lie at omega 1, omega 2 and omega 3. Here you can see the poles are going to lie at omega 3, omega 1, omega 2 and omega 3. So the closed loop poles are given by the characteristic equation 1 plus A beta. So already we know that for a closed loop, we are going to write the equation as 1 plus a characteristic equation, as we have seen in the last slides. That is, the characteristic equation is nothing but 1 plus A beta is equal to 0. So in the place of A, so we are here, A means what here? A means the closed loop gain. What we have written here? A is equal to AOL into omega 1 into omega 2 into omega 3 divided by S plus omega 1 into S plus omega 2 into S plus omega 3. That is nothing but ACL. That is A. Here we are considering ACL as A. In the place of A, we are going to substitute this equation. So here, by substituting this equation in the place of A, we are going to get 1 plus beta into, we are going to write this whole equation here. So this we are going to write here, which is equal to 0, which is equal to 0. And then by solving that equation, we have, by solving that equation, how we are going to solve this equation? So we are going to take LCM, that the LCM will be S plus omega 1 into S plus omega 2 into S plus omega 3 will come to the numerator, and then total LCM we are going to bring this to right hand side. 0 into anything will be 0. This becomes 0, and this denominator will obtained here. So that is how we are going to write here equation. After that, we are going to multiply S plus omega 1 into S plus omega 2 into S plus omega 3. Then we are going to obtain this type of equation, that is S cube plus S square into omega 1 plus omega 2 into omega 3 plus S into omega 1 into omega 2 plus omega 1 into omega 3. So after multiplying and solving the equation, we are taking the common terms. So S3 term common, then S2 term, S square term, that is S cube term common, S square term common, and S term common, making common. So and writing other terms separately. So then we can get this equation S cube plus S square into omega 1 plus omega 2 plus omega 3 plus S into omega 1 into omega 2 plus omega 1 into omega 3 plus omega 2 into omega 3. So plus omega 1 into omega 2 into omega 3. Here we are going to take common this omega 1, omega 2, omega 3, and we are going to get 1 plus beta into AOL. So this equation is considering as, we are going to consider this equation as equation number 2. So beta into AOL can take any value between 0 for no feedback. Okay, beta into AOL can take any value between 0 and 1 for no feedback. and AOL for maximum feedback. So by considering this, and that means beta is equal to 0 and beta is equal to 1. So beta is equal to 1 means it will be maximum feedback, and beta is equal to 0 means it will be zero feedback. So that must be, here you can observe that the beta into AOL is going to lie between 0 and infinity. So we are going to observe this condition between 0 and infinity. We are going to observe when beta AOL is equal to 0. So this is the root loci function of beta AOL. By observing this graph, beta AOL is equal to 0, the roots are at omega 1, omega 2 and omega 3, lies on negative real axis. So see here, this is the negative real axis, this is the positive real axis. So here you can see that the roots are going to lie on omega 1, omega 2 and omega t at beta AOL is equal to 0. At beta AOL is equal to 0, omega 1, omega 2 and omega 3. Here you can see, you can observe that. So when beta is equal to 0, the roots are at omega 1, minus omega 1, minus omega 2 and minus omega 3, which lies on the negative real axis. On the negative real axis, you can see here these 3 points are on the negative real axis. So for small values of beta AOL, the roots lie on the left half plane with one real root and two complex conjugate roots. So if we consider beta value further more than 0 and less than 1, that means beta which is going to lie between 0 and 1, we are going to consider beta less than 1, then the roots are going to lie on the left half plane of the axis. So see here, the roots are going to lie on the, here you can observe in this graph, that is the roots are going to lie on point A and A dash. Here you can see A and A dash. So, and both are complex conjugate to each other, two complex conjugate roots with one real root and two complex conjugate roots. That is, two complex conjugate roots are A and A dash. Okay. So when beta AOL is less than the beta AOL closed loop, that is open loop function is less than closed loop beta AOL. So if beta AOL is further increased, beta AOL factor is further increased further, and that means again we are going to increase the value of further, we are going to increase the value of beta AOL. The roots going to move towards the right half plane of the right half plane of right half side of the S plane, which causes instability. So when the roots are going to right half plane, so this cause instability. So we can observe that the beta is going to lie between 0 and some value, 0 and some value. It must not be 0. If it is 0, it lies on the real axis, negative real axis. If it is beyond 0, it is having some real root and two complex conjugate roots. It is stable, you can say. After that, if we beyond increase further the beta AOL, then the roots are going on to the right half of the S plane. So this becomes unstable. So for that reason, for what values of beta the operational amplifier performs better, so that we are going to observe now. So let us consider A3 is equal to 1. Let us consider A3 is equal to 1, A2 is equal to omega 1 plus omega 2. So why we are going to consider this? So here you can see the equation. So here you can see the equation. Omega 1 plus omega 2. For solving this equation, that is equation number 2. So we are going to simplify that by considering this A1, A2 and A3 values. Nothing but here in the place of before this S cube, there will be, we consider it as 1. So then we are considering that as A3. A3 is equal to 1. In the place of 1, we are going to write A3. Okay, like that. In the place of omega 1 plus omega 2 into omega 3, we are going to write A2. in the place of this equation, so we are going to write a1, and in the place of this equation, so we are going to write a naught. So by writing that, that means we are going to make the equation simple. So by substituting these values in equation number 2, the equation becomes a3 into s cube plus a2 into s square plus a1 into s plus a naught is equal to 0. So to find the critical value of beta AOL, so here we are going to use the root stability criteria. So by using root stability criteria, so we are going to find the value of beta AOL. That means we are going to obtain the value of beta AOL. So what must be the beta AOL value? So that we are going to obtain by applying the root stability criteria. So what are the main conditions for this root stability criteria? All coefficients, all the coefficients, that is A3, A2, A1, A0 should be positive. So for obtaining this root stability criteria, these coefficients must be positive. So already in the above equation, you can observe that the coefficients are positive. And it must satisfy the other condition, that is condition number 2, that is a2 into a1 minus a3 into a0 must be less than or equal to 0. That means the product of a2 and a1 and minus a3 and a0 product must be less than or equal to 0. It must be less than 0 or it must be equal to 0. That means we can say that the product of a2 a1 must be equal to a3 a0. We can say that from this equation we can say that the product of a2 and a1 must be equal to a3 and a0. Okay, here you can see that a2 is omega 1 plus omega 2 plus omega 3, and a1 is omega 1 omega 2 plus omega 1 omega 3 plus omega 2 omega 3. So these two, the product of these two must be equal to the product of a3 and a0. So when this condition is satisfied, so we can find the value of this beta. So keeping keeping here in the place of s, so we are going to write j omega in the place of s. So we are going to write the j omega. So the equation becomes a3 into j omega cube plus a2 into j omega square plus a1 into j omega plus a naught is equal to 0. So when by solving this equation, so by solving this equation, you can see here a naught minus a2 omega square plus why we are going to write like this means j square. J square is nothing but 1. Okay, so because of that reason we are going to write it as j square as minus 1. Okay, so we are going to write a naught minus a2 into omega square. We are going to take the term that as one term plus j omega into, okay, we are going to consider j omega cube. So j omega into a1 minus a3 omega square. So here we are going to take common j omega. Omega common, as we have taken the omega common, we are going to get inside we are going to get a1 minus a3 omega square. So a1 already, a1 is having the term j omega only, so we are taking that as common, and in the place of j3 omega, so we are going to write a3 omega square, which is equal to 0. So next, equating the real parts and imaginary parts. Here we are going to consider this as the real part and this as the imaginary part to 0. So we are making this real part, equating real part to 0 and equating this imaginary part to 0. So a naught minus a2 omega square is equal to 0 and a1 minus a3 omega square is equal to 0. So both we are making this both imaginary and real parts equating to 0. frequency of oscillations. Okay, this equating to 0, and we are going to find the omega value. So here the omega value is equal to, so for obtaining the omega value, so we are bringing this term to right hand side, and this becomes positive. So then omega is equal to a naught by a2, nothing but omega is equal to a naught by a2. So here we are having omega square now. That is why we are going to obtain omega is equal to plus or minus root of, square becomes root, so root of a naught by a2, a naught by a2. And this can also be obtained, omega can also be obtained by a1 and a3 also. So that is nothing but omega is equal to, we can write plus or minus root of a1 by a3 also. So keep this as equation, another equation. And then if we consider a1 by a3, if we consider this equation, then a1 by a3, already we know that what is a1 value, as we have considered there, let a1 is equal to something, a2 is equal to something like that. We are going to substitute this. So we have considered that a1 is equal to omega 1 into omega 2. So here you can see a1 is equal to this, a3 is equal to 1. So we are going to substitute these values here. So this becomes root of omega 1 into omega 2 plus omega 1 into omega 3 plus omega 2 into omega 3. So from the equation 3, we have, what is this equation 3? Root stability criteria. So this. So from this equation we can write a2 into a1 is equal to a3 into a0. Already we have discussed this. So from this equation we can write a0 is equal to a2 into a1 divided by a3. So that's what we are going to write here. a0 is equal to a2 into a1 divided by a3. So that means in the place of this we can write this equation also. In the place of a0 we can write this thing. So from the equation 3 we can write like this. So omega 1 into omega 2 into omega 3 into 1 plus beta AOL into C, which is equal to omega 1 into omega 2. That means a naught. In the place of a naught, we are going to write this equation, and we are going to write a2 a1 by a3, as a3 is equal to 1, a2 into a3. This is a2, this is a3. So then beta AOL into C is equal to, by solving this equation, so finally we are going to get beta AOL into C, that is a closed loop voltage gain, which is going to be, that is a loop gain, which is equal to 2 plus omega 1 by omega 2 plus omega 1 by omega 3 plus omega 2 by omega 1 plus omega 2 by omega 3, omega 3 by omega 1 plus omega 3 by omega 2. So we can say that the amplifier should remain stable for any resistive network, that is when beta value is going to lie between 0 and 1. So when beta lies between the beta value, the transfer function, nothing but the transfer function, which is going to lie between 0 and 1, then we can say that the operational amplifier is going to perform better. So AOL must be less than, AOL must be less than 2 plus this value. It's 2 plus omega 1 by omega 2. This, what is this value? So we're going to write here. So if beta value is must be 0 and 1, so that will be very small. So the open loop voltage gain must be less than this value. So we have to consider this thing. So why we have observed all these things, why we have done this equation solving, and why we are going for this stability criteria means, so yet what frequencies and for what beta value the operational amplifier is going to perform better. So for that reason we are going to consider this stability criteria, and we are going to obtain the value of beta. We are going to obtain the value of beta. So by obtaining this, so we can, so this is the stability criteria for an operational amplifier. So in the next class, we are going to discuss about the frequency compensation for an operational amplifier.